So what's up mga ka-ChE? It's Kuya Dale here. Saba kayo mga iro. Pwede mo hilom ng mga iro.
A few minutes later.
So what's up mga ka-ChE? It's Kuya Dale here and I'm back with another chemical engineering lesson. So we are finished with chemical engineering calculations. So now we're moving on to another field in or subject in chemical engineering, which is the favorite of all, chemical engineering thermodynamics. So I hope you can relate when I say that I passed ChE Thermo in college without understanding it. Diba? So shout out to my friends, so especially to my juniors. So silang Lauren, Erica, and Crystal Jane Pante. So believe me when I say the thermo in the review is much easier than the thermo in the undergrad. Okay, so I will prove it to you in this lesson. Okay, so without further ado, I also I want to shout out my classmates in QRC, especially I want to shout out pwede mo hilom na mga iro.
One eternity later.
Shout out din sa mga classmates ko sa QRC, especially those who came from XU who have answered my questions there when I asked them the thermo questions. So especially Daniel Joshua Beha, shout out sa'yo. You're so persistent in answering these questions. So I've compiled this for all of also the reviewees that will view this video. Okay, so I hope you'll enjoy it. Let's without further ado, let's begin. Okay, so our next next installment in our series, the ChETorial series, will be the chemical engineering thermodynamics. So welcome to this new lesson. Let's begin. So we are asked to solve first the Joule-Thomson coefficient, or the mu, K Kelvin per with the units Kelvin per MPa. So if a chlorofluorocarbon, we don't know what it is, but we are given the CP, or the heat capacity at constant pressure. So 0.6923 kilojoules per kilogram per Kelvin. So using the following data at 25 degrees Celsius. So we are given these values, and then we are to find the mu. So in order to find the mu, so we have to do linear regression. So to do the linear regression, so we have to find out what is the y and also the x component. So that's easy. So the y component is the h, and then the pressure is the x. Okay, so then we have to find the mu. The mu, and mu is actually 1 over Cp, and then the slope dP at constant temperature. Okay, so that's actually the formula for your y, your for your mu. Okay, so in order to find that, so you have to put it in your calculator. So linear regression. So in your calculator, just press this mode 3 and then 2, mode in 3 2, and then you will see the x and y. So input x in your in MPa in x, and then input the h in your y, and then if you finished inputting these values, you will press AC. Press AC, and then you will find it, diba, 0, and then after that shift 1 5 and then 2. you will find the value b, diba? B is actually the slope in our values in the graph, diba? So if you uh, get the value of that, so b then equals, so you will find b or dh per dp uh, is equal to negative 19.91 kilojoules per kilogram MPa. Okay. So you will have to find now you can now solve for the value of mu. So mu is 1 over the Cp, so negative 0.6923. You have kilojoules per kilogram, and then per Kelvin, and then multiply that by the negative 19.91 kilojoules per kilogram MPa. You will get 28.8 Kelvin per MPa. Okay, that's the answer. That's the answer for our first problem. So next problem, we have here a 0.4 milligram sample of liquid ethanol was burned in a bomb calorimeter, resulting to temperature rise of 2.86 degrees Celsius. How to calculate the molar heat of combustion of ethanol at constant pressure if the heat capacity of the calorimeter is 4.15 kilojoules per Kelvin and the mean temperature of the calorimeter is 25 degrees Celsius. Okay, so we have to write the givens first. So we have the mass of our ethanol, which is 0.4 grams or 400 milligrams. And then we have the temperature change, which is 2.86 degrees Celsius. And then we have our Cp of the calorimeter. We have 4.15 kilojoules per Kelvin. Then we are asked to find the H ethanol, diba? Molar heat of combustion. So molar heat of combustion. So actually, this does not require so many a formula, but we have to do it by dimensional analysis. So to find that, we have to analyze it. So we are asked to get the molar heat of combustion. So meaning the units must be in kilojoules per mole, kilojoules per mole. So we have to have the kilojoules in the numerator. So we have 4.15 kilojoules per Kelvin there, and then we have to multiply it by the temperature difference. So that's the temperature difference, that so it's equal to the Kelvin pod niya temperature difference, di ba? So that's equal, and then we have to divide it by the mass, but this will result in grams, but to get it in moles, divide it by the molar mass. Okay, then you will get the answer 1367 kilojoules per mole. Okay, and this is actually a exothermic combustion, so it's also this answer is also accepted. So because it is the heat is evolved, diba? So negative ang sign niya. Okay, so next we have the problem here. We have 2 moles of nitrogen gas which obey the van der Waals equation of state. So we have the first state in temperature 250, and then volume 5 liters, temperature second state is 100K. Then CV, 8 joules per mol K. A, which is the factors in the um, constants na siya sa van der Waals equation, and then letter B. Okay, so what we are asked the change in internal energy uh, accompanying the reversible expansion of this gas to a final volume of 80 liters, and then if the expansion was adiabatic, what is the final volume of the gas? So we actually have to we have no definite form of the um, definite form of the internal energy. So internal energy actually is di ba? U mana delta U. So we don't have the definite form of that equation yet, but now we will derive that, di ba? So let us write the given first. Let me write like right here. So we have 2 moles, and then we have the T1, which is equal to 250 degrees Kelvin. T2 is equal to 100K, and then V1 is equal to 5 liters, and then V2 we are asked 80 liters, ba? Then CV is equal to 28 joules per mol K, and then we have our A is 1408, letter B 3.913 times 10 to the negative 5. Okay, so we don't have it yet, the equation, but we have to we can find the equation here in our Paris. So this is equation for equation 4-34 in your Paris. It's actually in a table, so that's what we are the first form of your first law of thermodynamics that we will be using. Okay, so it's in the differential form, so don't freak out, right? Du is equal to cv dt. That's the form of differential equation that we will be using. Okay, and then we were told that this is a van der Waals gas, diba? So van der Waals is actually um, in this form, RT over V minus B minus A plus V squared. Okay, so we have to plug it in this part of the equation so that we will use it. Okay, so be we will get the partial of P with respect to partial derivative of P with respect to T first. Okay, so partial of P with respect to T with V remaining constant, held constant. So just differentiated with respect to T. That's it's actually simple. So T R na lang nabilin, and then V minus B, and then this term has no T, right? So treat it as a constant, and then it will be will be reduced to 0. So what happens now if you substitute this term here and then this P here, this is what will happen. Okay, so du is equal to cv dt plus rt. We have v minus b, and then if you plug it here, this P to there, we will have a negative RT over V minus B plus A V squared na dV. Okay? So this will actually cancel, di ba? Because they are they have opposite signs. And then you will have du is equal to cv dt t plus a over v squared dv. Okay, so that's, remember that form of the van der Waals version of the internal energy, because we will use that later in the other problems. Okay, so what you will do now is that you will have to integrate CVdt plus a v squared dv. Let's integrate this from T1 to T2, and then from V1 to V2. Ba? So it's actually simple integrating that. So we have CV T2 minus T1, and this will become minus na. Diba? Just remember your integration rules. So V1. Okay, so that's the form now. And then we will change that to delta na siya. Okay? Change that to delta na. So, and then you will have to, because these are in molar, diba? So, just put it n there, n. Put n. And then this is also n squared, diba? N squared na siya. Okay? So, you will have to substitute now. So, we have 2 moles, diba? 2 moles, and then we have 28. And then we have 100 minus 250 minus we have 2 squared times 0.1408, and then the convert the volumes from liters to cubic meters. So to do that, you'll just have to divide the values by 1000. So what happens now, it will be 80 liters will become 0.08 cubic meters, and then 5 liters will become 0.005 cubic meter, like so. And then we have negative 8,294.4 joules, or we are asked to convert this to kilojoules, so just divided by 1000, and then you will have 8.3 kilojoules, negative 8.3 kilojoules. Okay, so that's how easy it can be. So that's how easy we can solve these problems. Okay, so and this is letter A, diba? Letter A. This is letter A. So we are asked to find now for the letter B. So we are asked to find the final volume of the gas if the expansion was adiabatic, diba? So now I will have to delete this part of the this part of the solution. I hope you've copied it. Okay. Okay. So now let's go to letter B. Diba? So we have to begin with the first law of thermodynamics also. So we have du dq plus dw. Okay, so we are told that it was adiabatic, diba? So if it is adiabatic, it will the dq term will be 0. And then we are left with du plus dw. Okay, so we have du here, diba? Kana siya. Muna na atong du. Kana. But we don't have yet our dw equation. So dw is equal to negative px dv. But our p is not constant, it is variable. And the variation of p follows the van der Waals equation. So we have to substitute this p to this p so that we will find the work na term, na? So dw is equal to negative nRT. Let's put n na directly. So VNB plus n squared a v squared. Then let's ako nang I've already taken into account the signs already. So negative, imbis na negative din siya, yung siya positive. Okay? Okay. So next, we will have to put this together in this term, diba? Substitute that our dw here and our dw here and the du our du here. Diba? So we have cv dt plus a uh, v squared. Let's put n squared there, and then n here uh, is equal to negative nRT over v nb plus n squared uh, n squared, you have dv here, a, then v squared nb. Okay, so we have similar terms. You can cancel both sides, see, kini and kini, diba? So we are left with n cv dt and negative nr t dv, that's dv, v minus n b. And then we can actually cancel these n's here, and then t, because this is variable separable differential equation, you can put t here, diba? cv dt. So cv dt over t, and then we have r, negative r vnb db dv. Okay, we can integrate now. We can integrate from t1 to t2, then v1 to v2, diba? v1 to v2. And then, so what will happen there if you evaluate? So we have ln t2 over t1 is equal to negative r ln v2 and v1 n minus nb minus nb. Okay, so that's actually it. And then substitute all the given. So we have 28, diba? 28, then ln 100 over 250, and then you have a negative r, which is your 8.314. This is actually in your calculator, shift constant 27. Okay, and then 8.314 ln v2, diba? Bilang v2, that's what we are finding, diba? v2. And then we have n, which is our 2, and then b, 3.913 times 10 to the negative 5, and also v1 0.005, diba? 5 minus 2, then 3.913 times 10 to the negative 5. Okay, so shift solve to find v2. Then you can find v2. I'll put it here. I will convert it to liters na already. So you can find 107.8 liters. So the derivation is fun, di ba? The derivation is fun. It's not really difficult. Okay, so that's it. That's for the third problem that we will be solving. And then we will solve the fourth problem. So it's a four-part, diba? Four-part problem. So we have to calculate the work done by a sample of 0.10 mol neon gas that expands isothermally from 0.06 to 0.6 to 1.2 liters at 0 degrees Celsius according to the following conditions. So we have a constant external pressure of 0.9 atm against variable pressure which varies with volume according to the expression PV to the n, then equals K. K is actually a constant with the given data, so we can use that later. And then reversibly assuming gas is ideal, this is actually the simplest because you are doing the we are using the ideal gas equation. And then reversibly assuming gas obeys van der Waals. So van der Waals is again in the mix, okay? Van der Waals equation of state, and then we're given the A and the B. Okay, so let's go. Let's write the given first. So we have an Rn is equal to 0.10 uh, mole neon, and then we are given the isothermal, di ba? Isothermal. So meaning the dt term is equal to 0. So because it is not changing in temperature, di ba? So it's isothermal. So dt is equal to 0. And then we have our V1 is equal to 0.6 liter. And then we have our V2 is equal to 1.2 liter. And then we have our T is equal to 0 degrees Celsius or 273 Kelvin. Yes. And then letter A, we are given the condition that our external pressure is equal to 0.9 atm. Diba? This is actually simple. Diba? So we are going for the work. Diba? Work daw ko, no, is equal to negative. This is the equation for your work, ha. It's equal to px dv. Good. Px dv. And we have to integrate that. So let's integrate this from 0 to w and then from v1 to v2. So you can find this w is equal to negative px v2 minus v1. Okay, so that's simple. It's 0.9 atm, 0.9 atm, but let's convert that to pascals. So let's multiply that by 101,325 325 pascals, and then we have our um, volumes here. Let's convert them to cubic meters by dividing them by 1,000. Okay, and then you will get the work as negative 54.7 joules. Remember that joules is equal to Pascal cubic meters. Okay, so I have a classmate that's named Pam. So that's how I memorized this. So Pam, hi Pam. Shout out sa'yo Pam, Ara Pamela Bulutaulo, if you're watching this. Okay, hi Pam. So that's how I memorized that. So Pam, joules is equal to Pam cubed. So yes, so let's move on to letter B. So let B is we are given the condition PV to the N is equal to K, diba? But we don't know what these are. But we are given the table, diba? We are given the table, this data. Kana tagaan ta ana. So we can actually form a relationship, diba, or an equation to this to find our N. So what this actually means is that we have P1 V1 to the N is equal to P2 V2 to the N. Diba? So just V, ang vira na ang may to the N. So let's find the N. Yeah? So P1, P2, and then V2, then V1. So I'll just transpose the terms to the side. Diba? And then just choose these two terms, these two values here, and these first two values here. Just choose those. So we will substitute as 0.194. So, di ba, ATM, so ATM and liters. So, 194 and then 0.134 and then 0.6, then 0.8 and 0.6. And then shift solve. Actually, you can solve for n, diba? Using logarithms. So it's no need to shift solve that. you can get the 1.2862 value of n. So let's go to the form of our dw, di ba? Or dw. So dw is equal to negative px dv. So let's integrate these, ba? So from 0 to w, and then px, we have to find the form of that equation, diba? So p, but we have it actually here. So p is equal to k over vn. So I just transposed a v to the other side. So you have k over vn dv, diba? So if you get your the integral of this is actually the integral of dv there is 1 minus n, and then v 1 minus n. Oh, diba? So negative n, this is negative n, diba? Then plus 1. So that's equal to 1 minus n. So just substitute that here in the under, diba? So we have negative k, and then v 1 minus n over 1 minus n. So this is let's enclose that in brackets, and then diba our the variable there are two varying values here, which is the pressure and then your volume. So let's evaluate them in both, so P1 V1 and then P2 V2. And then let's substitute the K here for PVN. So negative PVN V n minus 1 minus n, and then we have P2 V2. Okay, so simplify this equation, this expression here, and then you can get the PV. Na? PV is over 1 minus n, negative, and then evaluate that in P2 and then V2. So using that, and then you can get the final equation for our V is equal to P2 V2 P1 V1 is equal to 1 minus n. Let's lose this negative expression sign. You can reverse the signs there. P2 V2 1 minus n. Okay, so how easy we can do that. So let's substitute. We have P2 P1 V1 and P2 V2. So let's use these values that we got earlier. So, and then we will transform that to cubic meters and then to Pascal, so that we can get the J, or the Joule. Okay, remember this, joules is equal to PAM cube. Okay, so how do we get this? Let's 0.194 times 101,325. That's the Pascal. And then we have our V. Let's just divide it by 1000. So we'll get 0.0006 cubic meter over minus 0.079. Or you can actually use the last, diba? The last, because we are going for 1.2, diba? In the final volume. So we will use these values. So 0.079 and then 0.012 0012, and then don't forget to multiply that by 1.025, and then 1 over our n is equal to 1.2862, and then we have our work is equal to negative 7.65 joules. Okay, that's easy. That's easy for us. Diba? And then let me erase all the ones so that we can solve for C and D. Okay, so now let's go for C. So we are given that reversibly assuming gas is ideal. So gas is ideal, so meaning we are using the PV in RT. Diba? So in RT, I transform that because we are using it here. PX dV. Okay, so just substitute this here. We have nRT over V dV. Integrate that from V1 to V2. You will get negative nRT ln V2 over V1. Okay, then just substitute. You can get actually 0.10 and then R 8.314 times 273 Kelvin, and then ln 1.2.6, and then you will get negative 157.3 joules. Okay, that's easy actually. And then lastly, for our van der Waals, we have W is equal to px dv, diba? Px dv, but we are okay, let's write that px dv p x dv, but p is equal to nRT over v minus nb minus n squared a over v squared. Okay, so let's substitute that here in the negative. So nRT over v minus nb minus n squared a. Let's take care of it here, and then v dv, and then let's integrate that from v1 to v2, which is transform it to input this in your calculator na, diba? It's 0.0006 and then 0.0012. So you can get W is equal to negative 151 joules. Okay, that's actually easy. Substitute everything, then put it in your calculator, and then you will get negative 151 joules. Meaning this, all the values in our calculation has the negative sign, meaning work is done by the gas. Okay, so that's what it means according to our sign convention. So next, the fifth problem of our in our series today. So we have 20 grams of oxygen gas at 25 degrees Celsius. Then we are to expand it adiabatically and reversibly from initial pressure of 4 atm and from 4 atm to 8 atm, 0.8 atm. So assuming gas behaves like an ideal gas, so reversible, ideal gas, and then adiabatic. So dq is equal to 0. And then we have to determine the following: the final temperature of the gas in degrees Celsius, and then if it is constant, so constant, the pressure is constant, 1 atm, calculate the work done by the gas and its final temperature. So lahi-lahi man sila. So letter A follows these conditions and letter B has its own condition. Okay, So letter A is actually easy. That's actually A is actually easy. So this is adiabatic and polytropic. So ang iyahang adiabatic and polytropic, meaning uh, that uh, the temperature, the pressure, and the volume changes. Okay, so that's what it means by polytropic. Adiabatic means no exchange of heat from the system to the surroundings and vice versa. Okay, so if the condition is this, we can use the equations in our Paris equations P10 70 to 72. You can find there the adiabatic and polytropic na equations. So we have because we have our we are asked to find our T2, and then we are given that P1 and P2. We can use this form of that equation. So P2 over P1 is equal to T2 over T1, and then this is raised to that. And then because oxygen gas is diatomic na molecule, we can use the 1.4. So this is actually in the gamma for air. So it's the ratio of the Cp over Cv. So we can use this equation. So we are to find the T2, right? So P2 is equal to 0.8, and then we have our P1 4, then T2 is equal to we are finding that, and then we are the first the temperature is 298, and then 1.4, and then we have 0.4. Shift solve to find T2 equal to 188.15 Kelvin, or in degrees Celsius we have 85 degrees Celsius. That's actually easy. And then for the letter B, we have to derive our equation because the conditions are different. We have first law is equal to du dq plus dw. We know that dq is the zero because it is adiabatic, diba? And it is also reversible. So we are left with this. So n cv dt is equal to negative px dv. So since we are not given the cv, diba? We are not given the cv. But since O2 is a diatomic molecule, we can assume that Cv is equal to 2.5 R. And likewise, Cp is equal to 3.5 R. But what is useful to us now is this value, 2.5 R. Diba? So next, we have our N Cv dt. Let's integrate this muna from V1 to V2, and then T1 to T2. T2 minus T1 is equal to negative Px V2 minus V1. Okay? But our volume ang atong volume sa ihatag sa toa that are given to us are variable, di ba? So we will also make them variable also here in our solution. So V2 ba nRT1 as T2 is equal over P2, and then also likewise for V1 we have nRT1 over P1. Let's just substitute that here because we're not given the volumes, right? So we are given the pressure and the temperature. So let's substitute that here. We have N CV. Let's substitute that na. So So 2.5 R. Then T2, we don't know that yet, but we know T1, which is 298, diba? And then we have negative 1 ATM in the PXDV. So negative, then 1, so 1 ATM. And then substitute these values here. nRT2, P2, nRT1 over P1, okay? And then you can actually cancel like terms here, so N and R. So NR and R. We are left with 2.5 to T2 298 minus minus T2 over P2 is 0.8, diba? 0.8 plus and plus, so I've taken it into account na ang kuan. So let's lose the parenthesis here. So negative dayon 298, which is our T1 over P2, P1, which is our 4. Ha? Okay, so gi-multiply na nako ang 1 ani, gi-distribute na nako ang 1 na mo na mo siyang positive. Then shift solve to find T2. T2 is equal to 218.53 Kelvin or negative 55 degrees Celsius. And then we have our work, negative internal energy by NCV dt. Okay, so N is equal to diba 20 grams man, we have 20 grams of oxygen gas, and then divide that by its molar mass. And then we have CV 2.5 R, 2.5 R, just R is equal to 8.314 gihapon. And then we have T2, which is 218.53 minus T1, 298 Kelvin. And then you will get the work, negative 1032.4 joules. Okay, so that's those are the answers for our problem. So next problem, which is the last two problems that I will be solving in this part of the video. So this is actually easy. So we are asked to find the ratio of the coefficient of thermal expansion alpha and the isothermal compressibility KT. So it is equivalent to, so we are asked to find A over alpha over KT. But in the Paris, this is actually beta over KT, but they actually mean the same thing. So just find this in your Paris. It is found actually in equation 4. It is equation 4-130. You will find it is the partial of P with respect to T with V constant, diba? PTV, People's TV, channel 1. Okay, that PTV, that's PTV. So that's actually the answer of this. And then lastly, evaluate the expansion coefficient alpha for an ideal gas at STP. Okay, so yeah, finding this na karon. So this is actually easy. Find it in your Paris. So I found it in Paris. This is equation 4-127, and you will get the alpha, or this is actually beta in the 8th ed, the Paris. 1 over V times the partial of V with respect to T with P as constant, diba? So let's do that. So at ideal gas, so PV is equal to RT. So we will PV is equal to R over RT over P, and then we are to differentiate with V with respect to T. diba? So if we differentiate that, dv over t with p remaining constant, so mahimo lang ni siyang rp, diba? Kay constant man ang p. So what we will do is that is to substitute ba, and we have 1 over v also here. So 1 over v, di ba? Imo ra ni siyang ibalihon. So we have p over rt. And then multiply that with our what we got kay kini man. So p r r. We'll get 1 over t. And then ideal gas at STP. So meaning it is at 273 Kelvin. And then you will get 3.663 times 10 to the negative 3 inverse Kelvin. Okay? So that's how you get your expansion coefficient in for ideal gas at STP. So okay, so that ends the first part of the ChE Thermo. So next time I will be teaching you how to use your steam table, and we will solve one problem for that. Okay, I hope you found this video helpful, and please subscribe to my channel. So I'm very grateful for the subscribers. So we are now at 366 subscribers. So yes, thank you for all your support. Boss, maybe it will be 367, or but I don't know, I haven't checked it yet. Okay, so keep on studying ChE Thermo, and then you will find it is really easy. It's really contrary to what I have experienced in undergraduate. Okay, so all the problems, or not all the problems, but most of the problems I have encountered in the review are really simple. Okay, so and I hope that you will not give up on your studying. So as always, I ask you to please pray for us. Madayon na amo ang board exam this May 11 to 13, and please pray for us that we will pass this exam so that we will be engineers already. So that's it for this video. I hope you find this helpful. Please subscribe, like, and share this to your friends. Okay, and please hit the notification bell so that you will be notified of the new videos I am uploading every week. Okay, that's it. Bye, annyeong.